Hello, lovely people. How is everyone doing today? I am having a fairly chaotic morning so far, as you can probably tell, given our late start. But I finally have my tea, all of my camera is working, OBS is working, and we are ready to go. So today we are going to start our very first day of our new series, which is Unraveling Network Secrets. So what that's gonna look like for this week is, move my face over here. What that's gonna look like for this week is, we're going to start with kind of crash course introduction today. Tomorrow we're gonna go a bit more in depth on how routing actually works. And then we'll pick it back up next week with more stuff about routing and some like practical coding stuff about like how to intercept packets, that kind of thing. So a full schedule will be posted soonish. I have the schedules for the next 4 weeks worked out so far, so we do have a plan. And yeah, I think it's gonna be a good time. How's everybody else doing today? Hopefully a little less chaos than me at the moment. We'll go ahead and get started with our lovely PowerPoint, because I did make a PowerPoint, even though maybe I should have just winged it, honestly, Anyway, I have a PowerPoint, I like my PowerPoint well enough, and we're going to be using it. So yeah. Doop. Gonna move my face over here. Hey, Analog, welcome, welcome. How you doing? Number 1 gold medal. I do not feel like I deserve a gold medal today, but I do appreciate it. Hey, Marcy, welcome to chat. Hope everybody had a lovely weekend. Been on an Atla fanfic binge. Well, as always, feel free to drop recommendations over in the story sharing channel. I am always looking for new fanfics. I've been getting a bit into the Locked Toon fandom space, as far as fanfics go, finally, at long last. But still lacks that, like, comfort of knowing all of the tropes that are common here. Got your hair dyed! What color did you do? That's so fun! I need to redo my hair. It's getting quite, dull, and my roots are getting pretty long. Blue! Very fun. I've always wanted to do blue. Have yet to do it, though. Let's switch over to... Come on. I know you have it. Brr, brr, brr. Felt bad afterwards owing to a drive-through, and the person asked me what color you put in, but it was mixed professionally. You can always ask next time if you really want to know. But that's a pretty common, like, I don't know. When I ask people what color dye they use, about half and half the time, people have gotten it professionally dyed and have no idea. Why does OBS hate me? There we go. Apparently. Thanks, I appreciate it. Alrighty, so why is the internet like that? Great question. Oh, I forgot my papers. I need my notes. One moment. Also, my work desk space is such a mess today. I feel like every 2 weeks or so, I just crack and like have to do a total reshuffling of my entire workspace and like tidy it up and clean it. And then every 2 weeks, it gets to the same state. Am I going to share the slides? Yes, I am going to share the slides. Are these slides going to be great? The quality substantially diminishes the further into the PowerPoint you get. But now I have the structure of my slides and I have all of the default formatting and things, so the next one will probably be better. Yeah, so I'm also going to share this paper because it's super, super helpful. It's where I pulled a lot of the information from. We're going to get my face all big. So this is the design philosophy of the DARPA Internet Protocols, and I make reference to it a couple times in the slideshow, but this is where a lot of the information came from. The author of this particular paper, so this paper was published in 1988, and it was written by David Clark at MIT. He is the person who was responsible for the architecture of TCP/IP, took responsibility for it in 1981. So about a little, 8 years after the TCP/IP program got started at DARPA. So yeah, that's the that's our source. Yeah. Oh no, we have an ad break. So we're just gonna spit talk for a bit. Also, that should probably go here. And should be bigger. But that's okay. Oh no, that's the opposite direction. I know how mirrors work. I am a person who knows things. It's so weird. Normally my face is, normally my seeing of my face and the chat is over here, not over here. And so it's a little disorienting. Mirrors don't work. It's a collective hallucination. I'm not sure about that. Interesting theory. But yeah, we're gonna open up our slides. So, why is the internet like that? So this is what we're gonna be doing today. I'll warn you, we may not be able to cover too much of the OSI model stuff, but we will be going back over that tomorrow in more detail. So don't worry about it. If we don't hit it too much, it's gonna get covered. First off, we're going to talk about what this course is meant to be. Then I'm going to talk about me. I know that many of y'all already know who I am, but there are people who may be watching the YouTube videos, since I will be uploading these, who don't know who I am. So we'll be going over that. Then we are going to go over the outline of assumptions. We're going to go over the assumptions about the constraints for the design of the internet. Because these assumptions really shaped what the goals of the design of the internet could be. Then we'll go over the key goals of the internet protocol design. And then we'll wrap up for today by going over the OSI model, which is model for the internet and how it works, and compare that to the TCP/IP model and the 5-layer model, which are all just different ways of thinking about how the internet works. That's what we'll be doing. Thank you for the follow, Arif. Welcome. And we're gonna move that little floating box over to a different spot, because that's not gonna be a great spot for it to be showing up. Okay. So, what is this course? The plan for it is that it is a course that is combining the principles of computer architecture and networking with information security. So what that basically means is, like, we're going to be going over basically how networks work and how computers work. And we are going to be, throughout the course, we are going to be looking at those pieces of architecture through the lens of information security. The reason I've decided to do this is because I think that by looking at it through the lens of information security, it provides pretty fun opportunities for interacting with those architectural decisions and seeing the ways that they actually affect how developers interact with the internet and interact with computers. So I absolutely loved my computer architecture and networking classes in school, but a lot of the assignments had you implement parts of the architecture from the ground up. And while that was a very useful exercise to ingrain conceptually how they work, it didn't give me much of a basis for understanding how that architecture affected me, and what sorts of things I would need to consider as I built applications. And so I'm hoping that by adding this additional component of information security and like various exploits that are possible at different levels of the network stack, that it will help give that extra aspect that I felt was missing from a lot of my courses. Where can you find this? Here on Twitch, and also on YouTube. So if you want my YouTube channel, I'll use the command in Twitch. So you can follow me over on YouTube. I'll be uploading these VODs daily. But for those who are joining us live and want to be able to like ask questions live and things, it'll be here on Twitch. It will be running, so this will be 10 weeks. I have 10 weeks of material. I'm going to take a break somewhere in the middle. So it's going to run from today, February 20th, to May 1st. I'll be doing this. I'm actually going to change this. We're going to be starting these at 12 p.m., so that's noon. Let's say 12:05, because that makes it unambiguously not evening. 12:05 p.m. Eastern Time on Tuesdays and Wednesdays. So any questions about the course, what we're doing here, the point of it all? I don't know. Leaving space for questions. Also, tea of the day is a chamomile peppermint calendula tea. I am quite pleased to have restocked my herbs. Alrighty. Hearing no questions, moving on to who I am. I forgot to put my name on this slide. That would be important. I'm doing so good. Cats. I don't think I get the bottom of the stack joke. There can be no internet without cats. That is true. Okay, I understand. Yes, cats. Baseline for everything. There was that dude who would always... No, maybe he was a biologist, actually. There's this one person who's published a lot of influential work in whatever field he was a part of, and he always included his cat as a co-author, and the cat always got eliminated by the editors, but for all of his pictures, he would always pose with his cat and hold it up really close to his face sometimes so that they couldn't cut him out. Anyway, who am I? I'm Ellie Peacock. I run the business that is the Eclectic Library, and that's me. So I am a freelance educator, I think is what I would call what I do here on Twitch and on TikTok, as well as a software developer. I have 6 years of industry experience in software engineering, particularly, and that industry experience spans 2 different startups, a defense contractor, and some corporate work as well. So been doing contracting and professional work in the software space for a while. And then I got my undergrad over at Georgia Tech. My specializations for computer science were in computer architecture, systems and architecture, and in networking. So this course is kind of perfect for my particular undergraduate training, I guess. And then other thing from my experience that I just like to highlight is that I was one of the Google Scholars I was one of the Google Scholars in 2019. I did a project for the Perl Foundation where I was building a linker for their new language, Perl 6, which is now called Raku. And I maintained a blog during that experience. Feel free to check it out if you're interested in how in the world a person decides to write a linker in the year of our Lord 2019. Because nobody's really written those since like the late 60s and early 70s. It was an experience. It was a cool one. But yeah, relevant interests of mine are I'm very interested in the history of the early internet, and particularly, so a linker is part of the, don't yell at me for semantics here, but linker is what happens after compilation. So it's considered to be part of the compilation process. When you have a program that you've written, say in C or in Java, so languages that get compiled rather than get interpreted, what happens is you take the code and you convert it. You need to convert it over into machine language, into something that's runnable. So you have your compiler that does that. And one of the final stages of compilation is anytime you have used a function, for example, from another file, or anytime you've used a class or a function from a module or an external library, you need to go grab all of that code and pull it into your program so that the computer knows how to run it, right? So that's what my project was focused on doing, it was figuring out how to make it so that Perl 6 could be run as a compiled executable. So rather than needing to run it live in the command line in a standard interpreted way, being able to ship the executable form so that people don't need to have Perl 6 installed on their computer. Static or dynamic linker? My dream was for it to become a dynamic linker. Mine was static. Mine was a static linker. But yeah, so the linker is basically the part of the compilation process that looks at all of the places where you've used placeholder names, like, that's a confusing way to put that. The linker is the part that looks at all of the other files that you have referenced and points the compiler at them and says, hey, that's the chunk of code you need to pull in. It creates that dictionary, that lookup table. It was a really fun and challenging project. And I believe my work got picked up by Timo and by Niner, who are two of the other contributors on the Raku project, to get it to work with more modules. So mine was only able to work with a limited number of external libraries. And the next step was getting it to work with more libraries. Anyway, that's what I did. It was cool. I would love to revisit it sometime. But yeah. Don't need a linker if you just stick all your code in the same file. That is true. And that would be why most people need linkers, because who wants to do that? Yeah. Relevant interests. I'm very interested in the history of the early internet, in open source community culture, and in hacking/fracking culture, particularly in the early days of the internet and the early days of the web. Other stuff I'm interested in, I like cooking, baking, fermentation. You can see some of my jam that I made. I'm a big fan of sci-fi. Read just about anything, but sci-fi is a great love. And then I like quilting and visible mending, and these are some examples of that you can see. This is a quilt that I actually made for one of my professors at Tech. Hence the colors when he was retiring. Yeah, other things. I like other hobbies and things that are relevant to know about me. I like cats, and I like taking ugly pictures of my cats. So if you join our Discord server, you will get to see those with some level of regularity. So this is Luna. I particularly like taking pictures of cats that make them look like dragons. Oh, this is Calypso. She's 13. That's my cat. One of the cooler things extrapolated from being a member of your community is how much more valuable college is as education over job training. You know as much as you need to know about computers to do your job, but there's so much more to learn about computers. I think it's kind of a mixed bag, right? So one of the things that I think is a real shame about the way that we talk about college education as it relates to computers is we act like computer science prepares you to be a software engineer, and it absolutely doesn't. That's not the point of it. Computer science is about the conceptual and architectural understandings of computers and networks and the systems that you can build with computers and networks. Maybe how individuals wind up interacting with that if you're more on the UX side. Or, you can go lower and dive below the processor and look into like optimizations and algorithms of how the processors work. But computer science is very conceptually focused. Software engineering is not, for the most part. And it can be super, super helpful and useful, particularly as you get further on in your career. And if you want to like grow into like chief architect positions, that kind of thing, into technical management, technical product management, it can be really, really helpful to have that strong understanding of computer science and such, but it does not make you a good programmer. It just means that you understand how everything works together. So again, helps you a lot with like big major design decisions, but does not actually necessarily prepare you to be a good developer. And I think that's a very important distinction. Job training, things like boot camps, and that sort of thing are going to be much better if they are well done, tend to be much better at creating a person who is ready to hit the ground running as far as like coding is concerned. But it's probably not going to give them a ton of room for growth in expertise, because it's just starting you at a particular level in the network stack and saying, okay, this is all you need to know. Anything else you can figure out on your own. Sorry for getting up on a little soapbox. It bothers me a lot that I think that I have a huge number of advantages as far as understanding computers that did very much so come from having that strong theoretical understanding and conceptual understanding. I really wish that we didn't tell people who are graduating with computer science degrees that they are equipped to be software engineers, because they still need like a year's worth of training. Yes. I also wish college wasn't talked about as job training, because it's not. Like, I don't know, maybe for some fields it is, but for computer science it absolutely isn't. I wish we still had liberal arts educations that were valued in this country. Soapbox. Comp sci feels like ideology to software's praxis. I like that summary. Yeah. Okay, but we've talked about me and my cats, and my grumps. So now we will move on to kind of topics of the day. So first thing that we're going to go over is the architecture constraint assumptions present in the design of the early internet. So one thing that's important to keep in mind is that these design constraints were shaped by the fundamental goal of the DARPA project that was responsible for producing the TCP/IP protocols. And that fundamental goal was, as put in this paper, to develop an effective technique for multiplexed utilization of existing interconnected networks. To put that into more human words, the goal of this DARPA program was they already had ARPANET, and they had the ARPA radio, and they had the ARPA radio packet network, and they wanted to connect those together. And they wanted to do this in a way where if any other networks came into existence, that they could wire those into. So this was all shaped, all of these design constraints were shaped by the idea that we have some networks already, and we want to get them to talk. So, list of the assumed constraints. 1, as I said, it is necessary to incorporate existing network architectures rather than to rebuild the network architecture from scratch. Yes, exactly, analog. The idea that other people would build their own networks and want to hook into this. So, have to be able to use existing network architectures rather than rebuilding from scratch. part of this is a practicality sense of like reinventing the wheel and like building something from the ground up is going to take a lot more time and energy and money than just using the thing that's already in place and tweaking it to work. Number 2, they made a requirement that packet switching has to be used in this new architecture, not circuit switching. And we'll get into the difference between those two things in just a second. They also said that networks would be one of the design constraints that they asserted was that they would assume that networks were interconnected by a layer of packet switches, which they called gateways. And then finally, that each of these gateways would implement a store and forward algorithm for the packets. So they could trust these gateways to be able to handle sending things. Any questions here? Can you imagine how different the internet would be if number 2 wasn't true? The internet would be wildly different. The internet would be so wildly different. It'd be more like using pneumatic tubes, I think, if we're being honest, because pneumatic tubes would require dedicated infrastructure that was dedicated to sending a particular message for the entire time period that the message was in transit, which is not required by packet switching. Yeah, and this is the thing, is the reason that they assumed these design constraints was predominantly because they already had ARPANET. They liked ARPANET. People were comfortable with how ARPANET worked and already had an understanding of how packet switching worked because ARPANET used packet switching. And while there were some networks, such as like the X25 network that didn't do, I believe that's correct. Don't quote me on that one. I'm just checking my notes. Scratch that. Ignore the thing about X25 networks. That's going to come up later. But yeah, basically, everybody was already comfortable with how messages moved around within ARPANET. And so they wanted to do things in a way that was similar to what people were already comfortable with. So they made design constraints that did that. And then just because we're talking about ARPANET and it feels worthwhile to mention, this is what that network looked like over the period of time that the TCP/IP, over the period of time that the internet was being born. So originally, ARPANET only had to connect 4 nodes. That grew to include some long-haul transits over to New England, specifically to MIT and Harvard. And I don't remember the name of the last one, and the text is too small. Then grew up all and down the East Coast and landed on some stuff in the middle, too, including UIUC, Carnegie, University of Utah, etc. And it was in 1972, or it was in 1973 that the TCP/IP protocol began being developed. So it was when they hit this scale that they were like, what if more people start making their own little networks? That could be difficult. And then by 1977, we've got much larger expansion. So basically, people already knew ARPANET, needed things that would interconnect with ARPANET, so we set the design constraints on that basis. Sorry that I keep floating my head around the screen. I haven't found a good place for it. You know what? We'll just, gonna stick it at the top of the chat and just leave it there. There's my face. Okay. Yeah. So one of those things that I mentioned was packet switching versus circuit switching, and they decided that any design that was gonna work for their use case, which for what their main desire was, which was to develop an effective technique for multiplexed utilization of existing interconnected networks, they were going to just assume that they were using packet switching for design purposes. So let's take a step back and talk about what circuit switching is versus packet switching, because both are totally understandable design choices. And both have like their pros and cons. So circuit switching is more like how phones work. Like Analog just said, it's like a phone switchboard. So when you're using circuit switching, you need to provide a dedicated path for communication. So you have to say, hey, you have to have a method for setting up the line of communication. So saying, okay, Billy is calling Annie. And then you need to dedicate that line to them for the entirety of their phone call. For the entirety of their communication, that line only belongs to them. This has some pretty awesome benefits, including latency is really low because their messages don't have to compete with anybody else. Fred can't use their line. It's reserved for them until they decide that their communication is done. Performance, similarly, is very predictable because they have guaranteed bandwidth and physical hardware for the duration of their call. However, that does mean that it's pretty expensive because you have to have a bunch of dedicated hardware. And the scalability is limited because the number of simultaneous calls that you can have is limited by the number of lines that you have, right? Circuit switching is really, really, really good for real-time communication, like phone calls, because it has that dedicated dedicated hardware, the low latency, the very predictable performance, very good for real-time communication. Yeah, it would make multiplayer gaming way more robust if the internet was created with circuit switching. Packet switching, on the other hand, works more like the US Postal Service, where you can send individual envelopes into the system, and it will come out on the other end. It's a more efficient use of bandwidth because rather than having a dedicated line for the duration of a phone call, even if somebody, for example, say you're having a phone call over the internet, and there's a period of like 5 minutes in the middle where someone has set down the phone and run to the bathroom. During that 5 minutes, your system could be using that line to send data to someone else, right? A little 5-minute phone call could fit in there. But because you're using a circuit switching method, that line is already guaranteed to those two people until they decide to hang up. So with packet switching, that doesn't happen because you don't have that dedicated line, you don't have that dedicated hardware. If the person sets down the phone to use the bathroom, somebody else's messages can get through more quickly. Yay. Packet switching, it can handle a wide range of data rates and packet sizes. That's true. Whereas circuit switching, you're going to be pretty limited based on like what each of those individual lines can handle. Like the size of message that each individual line expects to have moving through it. Packet switching is kind of ambivalent about the size of the particular wire, because it can send a bunch of little packets through a big hose, and it can send one or two larger packets through a small hose as needed. Because of that, packet switching is more scalable, and makes it easier to share resources. However, that does have the trade-offs of it's much, much harder to implement a packet switching system that allows you to prioritize particular messages. So if you have the nuclear phone call and you really want to make sure that nothing gets dropped and that communication happens as quickly as possible, making a phone call over a packet switching system is not going to work great, because Billy Bob Joe Bob's message about when dinner is going to be ready might wind up hitting a particular node sooner than the president's message about the nuclear launch codes. That was a weird example. Yeah, so packet switching isn't as great for real-time communication because you have really no guarantee about how fast your particular message is going to move through the system as a baseline. Alrighty. So, now we have our overall fundamental goal. We have the assumed constraints, which is that we're going to be using packet switching, that we're going to make it possible for existing networks to combine together, that we're going to interconnect those networks with packet switches, and that the packet switches will be able to forward messages. We have those constraints. Now we have some more goals for the Internet Protocol design. So, first goal, again, our fundamental aim, multiplexed use, so multiple users being able to use the existing interconnected network simultaneously. Goal number 1. Our next goal, internet communication must continue despite loss of networks or gateways. Other thing that's worth mentioning is these goals of design are in priority order. This is the order that they mattered to DARPA and to the people who were designing the Internet Protocol. So, first one, multiple users being able to use a interconnected network simultaneously. The next one is resiliency. It's that communication over the internet must be able to continue despite loss of networks or gateways. So if a particular computer gets unplugged or a particular chunk of the network goes down, communication still needs to be able to happen. So this is where my PowerPoint gets less thorough because I ran out of time. Yeah, so we are getting worse at this part, and I think we're getting worse at this part because of social media networks and the consolidation of different parts of the internet. When you have 5 to 6 companies that everything passes through, if that company's network goes down, it's a bad time for everybody. So yeah, what this means is that if there is, they needed the internet protocol to work in such a way that if the internet connection was temporarily, if the connection between two nodes was temporarily disrupted, that the people who were trying to communicate to each other wouldn't need to reestablish a line of communication, that they wouldn't experience the fact that they had that temporary interruption. So the architecture had to mask transient failures, transient network failures. So what that means is that to achieve that goal of being able to mask those transient drops in network or loss of particular nodes, that kind of thing, is that the state information that describes the ongoing conversation has to be protected in some way. So some of that state information includes the number of packets, the number of packets that were sent, the number of packets that were acknowledged by the other end that were received, and the number of like outstanding packets still in the network. Because if that information gets lost, then there isn't a way to know. If that meta information gets lost, there isn't a way to know if there's been a data loss event. So at this point, there was a design decision to make. They needed to decide whether they wanted that information to be maintained within the network or if it was going to be maintained by the entities on either end of the network. And spoiler alert, they decided that that information was going to be stored with the entities that were trying to communicate. I'm grateful that they made this decision because it helps a lot with making sure that you have it helps with some of the privacy aspects of communication. Because it means that your network doesn't need to know like how many bytes are in the message that you're sending. Like each node doesn't have to remember that. But their concern, the reason they went with that choice was not because of a security mindset or a privacy mindset. It was because it was simpler. So I'm going to read a little chunk of the paper here. In some network architectures, this state is stored in the intermediate packet switching nodes of the network. In this case, to protect the information from loss, it must be replicated. Because of the distributed nature of replication, algorithms to ensure robust replication are themselves difficult to build, and few networks with distributed state information provide any sort of protection against failure. So basically, if you're having your network itself maintain that information about how many packets have been sent, how many have been received, all that kind of stuff, it can only maintain that and guarantee that by duplicating it a bunch. But you still have the issue of if node A has a copy and node B has a copy and node C has a copy, then what happens if node A, B, and C all go down? You still have lost the information. So instead, they opted for a method that was called fate sharing. And it's fate sharing means that they are making the assumption that it is, hey, Andy, welcome, welcome. What if the real treasure was the border gateway protocols we made along the way? Cheers. Welcome to stream. Yeah. Boop, boop, boop. What was I saying? Radio voice. We'll try to do some radio voice. Water a human? I don't have water. I only have tea. Does that count? Certainly is hydrating. Shared fate. That's where I was. Alrighty. Shared fate. Yes. Shared fate. The shared fate model suggests that it is acceptable to lose the state information associated with an entity if, at that same time, the entity itself is lost. What that basically means is that if Bob and Anne are trying to talk to each other and Bob's computer suddenly goes down, it's okay if the message between Bob and Anne gets lost. There are a couple of advantages to fate sharing. Number one, fate sharing protects against any number of intermediate failures, whereas replication only protects against as many copies as you make. So if there is an issue in transit, 3 nodes go down and you only made 3 copies, if those nodes are holding those copies, you're screwed. Whereas with fate sharing, you don't have to worry about intermediate nodes going down. You can just go around. Your message can just go around. Next, fate sharing is far easier to implement than to have every single one of your nodes have intelligence and statefulness. Instead, only your entities at the ends of the network have to. Any other important highlights from this section? We will see. So, consequences of this fate-sharing decision was that the intermediate nodes cannot be relied upon to have any sort of essential state information about ongoing connections. Yep, that's it. If different design decisions had been made, if this had had a higher priority level, different things might have occurred. The structure of the internet might be a little bit different. But different design decisions were not made. So here we are. So yeah, that's number 1. Internet communication has to continue despite loss of networks or gateways. Next one is the internet must support multiple different types of communication service. So this is where we start talking about TCP. So in the original thoughts, as they were designing the internet protocol, they actually combined the communication service and the internet protocol. So TCP was going to be part of TCP, and IP weren't going to be separate protocols. They were going to be one protocol. But, and the reason behind this was that one of the main things that they were needing the internet to be capable of supporting was they needed people to be able to do remote logins, and they needed people to be able to transfer files. And for both of those, it was very important that every single message that got sent through the network was received, and that it was received in order, which is the guarantees of the TCP protocol. However, there are other kinds of things that you need to do over the internet, And they realized that as they were developing the internet protocol. So an example, the very first one that they ran into of a type of communication that didn't have that same core need of in-order communication and guaranteed reception was XNet. So XNet was a network debugger. It was a cross-internet debugger. And if you are in a situation where you're debugging something, you are not going to want to rely on the system that you are trying to debug to be reliably sending information, right? You just want to get whatever information it's able to send out so that you can look at it and maybe get a better idea of what's going on. So TCP doesn't work well for that. Another thing is voice communication. For real-time voice communication, it's way more important, or video streaming. It's way more important that you receive the packets of information as quickly as you can, even if they wind up coming a little out of order, even if a couple of them get dropped. It's much more important for the packet of data to be handed off to the end user as quickly as possible, rather than that you wait until a dropped packet gets resent so that you can deliver it in order. Because having choppy voice communication is way more difficult than just missing a word. Does that make sense? So because they kind of had that realization with XNet, with the cross-network debugger, and they had the realization that they may eventually want to be able to support voice communication over the internet, they decided that they needed to have more than one, the internet protocol needed to support more than one transport protocol. That the internet protocol needed to work for transport protocols that prioritized different things, and some of those levers that could be pulled were like reliable sequenced data versus fast data. Some of those levers. So that's what caused the development of TCP, the separation of TCP from IP, and also caused the creation of UDP, which is the User Datagram Protocol. That was created in 1980, and that is the protocol that enables best effort. So UDP is what's going to be used for video streaming. What's going to be used for anything that you're doing real time is probably going to be UDP based. Imagine trying to market VoIP when people were used to picking up the phone when a modem was on the line and hearing screeching. God. But yeah. That's this one. They needed the network to be designed such that people could have different priorities as far as like what the communication needed to be its priority. Cool. Next one. Internet architecture must be able to accommodate a variety of networks. Needs to be able to accommodate networks that have less bandwidth available within them. So this is saying that the internet architecture had to be able to assume that it couldn't assume a particular implementation for the network, and it needed to be able to handle different speeds of networks and that kind of thing. Because at the point in time where this project, DARPA's project to develop TCP/IP, was being done, is it had there were a huge variety of networks that were already in existence. There were long haul networks that, went from California to New England. They had local area networks, so little Ethernet networks or ring nets. They had broadcast satellite networks. They had packet radio networks, serial links. So they had things that had very, very different specs and capabilities, and they wanted them all to be able to communicate to each other without trouble. So the way that the internet actually goes about, so they had to make some sort of decision that would enable these various networks to be able to talk to each other despite having vastly different capabilities, right? And so what they did is they decided on a base set of assumptions about the networks. So they made a list of, okay, these are the basic qualities that the network needs to have in order to be able to play nicely with other networks. Those assumptions were as follows. That the network has to be able to transport a packet, that the packet needs to be of reasonable size. So in this particular paper from DARPA, it says that, that reasonable size is maybe minimum 100 bytes. So your network has to have a tube that's at least some minimum size. And that the network needs to be capable of delivering messages with reasonable reliability. It doesn't need to have guaranteed always going to get it through the network, but it needs to have reasonable reliability. The messages need to get through most of the time. And they also very explicitly did not include certain things. Like they didn't include particular speed requirements because that would mean that those existing networks would need to be re-engineered. And that would cost a lot of money. They wanted to be able to use that existing infrastructure. So they decided on a small set of base assumptions that they could make about the networks and said, okay, that's it. Neat. What else? Give me 1 second, y'all. Hello, I am returned. Sorry, had to handle cat things. Where were we? Yes! Must permit, other goals. Next goal was that internet architecture must permit distributed management of its resources. This is not a thing that they actually did super well. Hi, returned. I'm Marcy. Nah. We will talk more about this one on a later date, but they kind of achieved this in that, like, all of the various ways to connect to the internet are not all managed by the same entity. There are different network providers. However, in the early days of the internet, it was relatively difficult to get those networks to interconnect. And we're actually going to be talking a lot about that on our Economies of Interoperability Day. Or the economics of interoperability. It's very, very cool. This is basically goal number 5. Because it was such one of the lower priorities, it's the reason why like tier 1, tier 2, tier 3 networks kind of came into being. And we'll talk more about that on a later date. Next one is needs to be cost effective. They did manage to achieve this because they were able to use, this one was mostly there as a reminder that they wanted to like reuse existing architecture and technologies. However, there were some aspects of the way that they made their designs that made the internet less cost effective than it might have been if they had made a different design choice. For example, if they had opted for circuit switching instead of packet switching, there would be far fewer instances where packets need to be resent, right? Because you have a guaranteed line of communication. You aren't going to have packets just go missing in the network. And so they kind of made a rule of thumb that, like, if you're looking at your network and you're dropping more than, like, if you're getting up into the zone of dropping like 10% of your packets that are coming through your network, you probably have a problem. Should probably fix something. Make your network more resilient. So they just decided, we can handle some inefficiency as far as number of retransmitted packets that happen through our network. The next design requirement was that internet architecture must permit host attachment with a low level of effort. This means if somebody wants to connect to the internet, it needs to be relatively low cost to do. Again, not super well achieved or not highly achieved. It is still to this day a little more painful than it could have been to connect to the internet. But because it was designed such that only the end entities need to be intelligent about how messages get sent through the network, about whether information has been dropped, that kind of thing. I'm gonna rescind that. Gonna slow down and correct myself. Because only the hosts, the entities trying to talk to each other over the network, have to store state information about the messages that are being sent. It means that the protocol only has to be implemented on the hosts. It doesn't have to be implemented on every single node that already exists in the network. So that helps quite a lot. It meant that, new people joining up would have to implement something once rather than, okay, we have to go through all of the existing nodes in the network and add new software to them and make sure that software stays up to date and all that. Like, just simplifies things a little bit. And finally, that the resources used in the internet architecture must be accountable. That it would be that you had to be able to trace down which individual hosts were using the most bandwidth and that kind of thing. Which again, because it was one of those lower priorities, because the internet was truly designed by the DoD to some extent, by the Department of Defense. They cared a lot less about the traceability of things than cared a lot less about the expense of individual usages of the internet than they cared about the ability to get a message reliably through the network. A different decision probably would have been made if the internet had been designed by a corporation for profit purposes. But it wasn't. It was designed by a bunch of academics and the Department of Defense. So. Okay. So, we're going to we've done the more in-depth description. We're going to just do a quick reread of the goals of the Internet Protocol design that shaped the Internet Protocol. Those are 1. Multiple users being able to use the existing interconnected networks at the same time. 2. Resiliency despite loss of individual nodes or gateways during communication. 3. Support of multiple different kinds of communications that have different priorities as far as speed versus completeness. 4. Needs to be able to accommodate a variety of different networks with different capabilities. 5. Needs to permit distributed management of resources that are part of the internet. That it needs to be cost effective. 6. That it needs to be cost effective. 7. That it needs to be easy to connect a new host to the internet, a new client to the internet. And 8, that resource use must be traceable. So these were the design goals of the Internet Protocol. And that is what resulted in the thing called the datagram, which is basically the packet and the description for that packet that is at the core of the Internet Protocol design. And we will be talking more about that exact packet structure tomorrow. With our remaining time, I am going to go over a little bit of the OSI model so that you know where the IP, where TCP and where IP, Internet Protocol, sit inside our idea of what the internet is and how communication on the internet works. So yeah. Basically, will I decorate a datagram cracker? That is a thing I could do. And would make a fun shitpost for Tumblr. But probably not. Thank you for asking, though, Andy. Sorry to disappoint. Okay, so a name like the OSI model probably sounds intimidating, or might sound intimidating. It's not, I promise. The OSI model was an initial description of how they thought the internet should work. How they thought that networks should work. And I'm gonna give you a spoiler here. Very few people actually think about the internet in terms of the 7-layer OSI model anymore. They use one of these other models to talk about the structure of the internet. They either use the 5-layer model, which is often called they either use the 4-layer model, which is also called the TCP/IP model, or they use the 5-layer model. But we're going to go through OSI because that's where people tend to start. So at the very top, we've got the application layer. You know what? We're going to start from the bottom. I think it makes more sense from the bottom. At the very bottom, you have your literal physical wires. So this is the physical layer. This is going to be literally your Ethernet cables or your coax cable. It's going to be your wireless connection, your Wi-Fi connection. It's the physical structure that connects the physical parts of the network. The physical hardware of the network. Your next layer is the data link layer. God damn it. I said a confusing thing. I said Ethernet cable. Ethernet is a protocol. The cable is... Okay, I'm just going to start over. Your bottom layer is the physical layer. It is the physical wiring, the wireless connection between your phone and your modem. It is the optical cables the fiber optic cables that are buried under your street. It is, the Cat5 or Cat6 cable, which is what Ethernet runs on. It is the physical hardware. Next up, we've got our next level, which is the data link level. And this is where we're actually sending little bits of information through the physical level, through the physical layer. So this is where you've got your Ethernet protocol, that kind of thing. We will talk more about the data link level layer potentially. Actually, we probably will not touch on the data link layer particularly much during this course. Except for maybe some ways that you can exploit it, but probably not. Next up from there, you've got your network layer. So the data link is really just the interface between your network level, which is the IP protocol, and your physical thing. So you need to have something in between those, the data link layer, because nothing in the network knows what physical hardware it's running on, right? So you need something in between that says, okay, we have this IP packet. I need to get this to send to computer B on my network. I need to get this to send to computer B over copper cables. And And that's what the data link level does. Okay, so now you have your network layer. This is where you've got the IP protocol and the datagrams, which we'll go in more detail about. All of the stuff that we've been talking about so far has to do with just this network level. Then we've got our transport level. That's TCP or UDP. That's the level that says, that handles like the way that two entities that are trying to communicate with each other. I'm going to drink some water. The transport layer is what handles what you pick in the transport layer to be using is determined by what your end hosts care about as far as reliability versus speed. Then you've got your session layer, which I'm just going to read off of the... Sorry, my brain's really taking a hard hit right now. Yeah, in the transport layer, you're handling things that have to do with end-to-end connections and reliability. At the session layer, you are handling inter-host communication. So that's going to be like which socket information is coming into, sending stuff from socket to socket. Then you got your presentation layer, which is going to be particular encodings of information. So whether you're using a JPEG or a PDF, or if you're communicating over Telnet or SSL, this is the layer that's responsible for unwrapping that. And then at the top level, you have your actual applications. This is the thing that the end user is using to send things. I know that was not a great way that was not like a really thorough explanation of the OSI model. We will go into it more tomorrow. Just wanted to show it to you and have it start percolating around in your brain. I am kind of a fan of the 4-layer model, is how I tend to think of things, because those top 3 layers, application, presentation, and session, are all a little bundled together. It's the stuff... Application, presentation, and session is all of the stuff that needs to get handled before you shove it into the tube that is the internet, right? And then as far as stuff below the network level, the combination of the data link and the physical layer, honestly, those are quite similar. Data link is basically the API to the physical hardware. And so it makes sense to me personally to combine those. In more recent years, the 5-layer model has been most popular, I believe. So still having that separation between the data link and the physical layer. I don't tend to work that low in the stack. So the people who do know better than me and have seen fit to keep them separate in the layer model. So I will trust them. But yeah. And that is what we've got. Any questions? I know that was a huge quantity of information. Also, I've decided that every unit that we do, we're going to have a cute little friend that is from some sort of ancient manuscript This one is a dude from an Icelandic manuscript who maybe is supposed to be a whale. I'm very excited. I need to give them a name. Yeah. We covered a lot of things. We are, of course, going to be diving more in depth on particular parts of this. But let's go back to the table of contents. Yeah. So we have an idea of what the course looks like. We have gone over what the key goals of the Internet Protocol design were and why they were prioritized in that order, and the effects of prioritizing them in that order. And we've done a very brief overview of the OSI model. I'm glad that you're glad that you saw cats. Oh yeah, you came in after the cats. Cats, 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 cats. They're good cats. Encapsulation is a good reason why. Indeed. But yeah, that's stream today, folks. So as a reminder, I'm gonna drag y'all over here so I can see you more easily. Sorry for the infinite. Don't worry, this time I am actually for real uploading it immediately after stream, so it will be there. And tomorrow, we will be talking about how IP routing works and looking specifically at the datagram structure, etc. So tune in tomorrow for that. This time is wrong. We'll be starting at 12:05 p.m. ET. So yeah. And with that, I'll catch y'all tomorrow. Have a wonderful rest of your day.